Hello, welcome everybody. So we're starting chapter 10. This is the gas law section, and we're going to focus on just utilizing the gas laws to solve some problems. And this is part one of two parts. Okay, so gases, they're made up of atoms or molecules that are going to bounce off each other or the walls and create a pressure in a box. So you can see that shown here, the atomic view. The motion is random. There is an assumption that there aren't intermolecular forces that are keeping them held together. Later, we can see that there are actual real gases where that does exist. But mostly what we consider gases are these particles that are just moving around at random, hitting the sides of a container. And it's that hitting the sides of the container that creates a pressure in that system. So when we have a gas in a balloon, number one, two things are going on here. If the gas is lighter than the air around it, if there's a lighter density, less density, then a balloon, for example, filled with helium will float. The other thing that we consider here is the pressure of the balloon. The reason why it's being expanded to a certain volume and held with a certain pressure is the amount of particles in it, the temperature of those particles hitting the sides of the walls of the container. Same thing with your tire in your car. On really cold days, sometimes my indicator light for my tire goes off just because there's less collisions of those air molecules in the tire pressing up, creating that pressure for that tire. So you can see there are a lot of variables at play here. The first thing I want to do is talk about what gas pressure really is. Pressure is force over area. So when we talk about atmospheric pressure, what we're really talking about is the pressure of gas molecules above us in the atmosphere pushing down on us. And you could think of yourself at sea level as well, pushing down on us by the force of gravity. So at sea level, there's an atmospheric pressure of 1 atm, and that's a unit. If you're at the top of a mountain, however, you're high up, so there's less gas particles above you. So the atmospheric pressure there, the pressure is less than 1 at sea level. Okay. There are a couple units of pressure that you will be exposed to. The atmosphere, millimeters mercury, and torr are the ones that we'll be using in this class. There are other units of pressure, pascals and psi, pounds per square inch, which you may be familiar with, maybe using in physics, but I'm not going to use that in this chapter. 1 atmosphere is the same as 760 millimeters mercury. So that you can use as a conversion factor. If you're given millimeters mercury, you would use, okay, 760 millimeters mercury are in 1 atm, and you can go ahead and convert to get your pressure in atmospheres. The other thing is the torr unit is sometimes used. That's the exact same thing as millimeters mercury. Torricelli was a scientist that did an experiment where he inverted a test tube filled with mercury. At 1 atm, the height of the mercury went up 760 millimeters. So that's where it comes from. But be able to do those conversions, and you can practice that. What I want to talk about are 3 different gas laws that will culminate into the ideal gas law. These laws really explain physical behavior of gases based on certain variables, such as pressure, which I'll abbreviate P, temperature T, volume V, and the number of moles N. The first law is Boyles Law, which says at a constant temperature, so we're going to hold certain variables fixed. In this one, we don't mess with the temperature. The volume of a fixed amount of gas, so the number of moles of gas is also constant, is inversely proportional to pressure. What that means when someone says it's inversely proportional, what that means is when one goes up, the other goes down. So let's look at this. If I have a gas in a cylinder at a certain pressure, so here I have a volume of 1, a pressure of 1, it really doesn't matter. But what you'll see is if you increase the pressure, and here I'm just going to make a weight twice heavy enough to create a pressure of 2, so double the pressure. What that does is it squeezes that volume smaller. So the volume is halved. You could think about it another way. What if you decreased the volume? Let's say I started out at a volume of 1 and I just decreased the volume to 1/2. Then that means the pressure must have doubled just because they're inversely proportional. So let's think about that at the molecular level. You have a container of a gas. You have to start thinking about these are particles just bouncing around at random, hitting the sides of the container. That creates this pressure of 1 atm. What happens if I have the volume? So now look at the particles. They're not all spread out. They're now confined to a smaller space, so they're going to hit the walls of the container more, which will increase the pressure. So that's how you want to start thinking about this. How you write that can be this way. Volume is inversely proportional to, I apologize, is directly proportional to 1/p. So the symbol here means directly proportional. If you want to say something's inversely proportional, you would say 1/something. Okay, so it's directly proportional to 1/p. As volume decreases, pressure increases. Or you can say that P times V equals some sort of constant, meaning if I decreased V to maintain that constant, I would have had to increase P. Okay, let's go to the second law, Charles's law. At a constant pressure, the volume of a fixed amount of gas is directly proportional to its Kelvin temperature. That Kelvin temperature part is important. It's not in Celsius. These gas laws only work if you're in Kelvin temperature. So you could write that volume is directly proportional to temperature, meaning if temperature increases, volume increases. If temperature decreases, volume decreases. You can also write that as V/T is a constant. And let's just look at that. Consider a gas in a cylinder. Here I have a temperature of say 200 Kelvin. I have a volume that's 0.5 liters. If I double the temperature, I increase that temperature, what I observe is the volume doubles. So that is directly proportional. I doubled the temperature, the volume doubles. Think about that. Does that make sense to you on a molecular level? If you increase the temperature of a container of gas, what does that do to the overall energy in that system? It increases that energy. Will the molecules be moving faster or slower? They'll be moving faster, meaning they're going to be moving faster, hitting the walls of the container more. That would have resulted in an instantaneous or temporary increase in pressure. But since this is a cylinder where you can expand it, that increase in pressure, similar to a balloon, will result in an increase in volume. Last law, Avogadro's law. At a constant temperature and pressure, so we're holding those constant, not changing those, the volume of a gas is directly proportional to the amount of gas. So V is proportional to N. If I increase N, V will go up as well, or V/N is constant. Think about blowing up a balloon. You use 1 mouthful of air to blow up a balloon. You only get a small amount of balloon volume increase. Use a second, a third, etc. More mouthfuls of air, increasing the moles of gas, then that increases the volume. Similar concept as increasing the temperature. If you add more gas to the system, you're increasing more particles are going to hit the walls of the flask or balloon more. So it'll increase the pressure momentarily, and it'll want to release that pressure by expanding, if you can expand, and a balloon can expand. Okay, if we sum all these up, we get what's called the ideal gas law. We get PV equals nRT. And basically, we just took all of these laws where you can actually rearrange this and show P times V over N times T equals some constant R. If we plug in real numbers for gases, a specific number of moles at a temperature, a volume, and pressure, we can solve for R and get 0.0821 liters atmospheres divided by mole Kelvin. These units are important. We're going to be using the ideal gas law, and the required units are pressure in atmosphere, volume in liters, N in moles, and temperature in Kelvin. If you don't use those units, this will be wrong, because that's how the ideal gas laws work, and R itself is in those units. So those units will need to cancel. The reason why it's the ideal gas law is ideal means perfect. So we're assuming that gases are behaving in a perfect manner, where they're not interacting with each other a lot, their volume isn't super huge compared to the container, etc. We're going to explore that a little more in part 2. So we're going to be able to use this equation, do some basic stuff. For example, given 3 of the variables, you could solve for the 4th. The other thing is we need to look at how conditions change over time. For example, if you have an initial set of conditions and then later on you change those conditions. So I'm going to show you that we can use either the ideal gas laws. For example, if volume and temperature only change, everything's held constant, V over T is a constant. And in that case, you can say, oh, if V over T is a constant, then the V over T of one situation is V over T in any other situation. So we're going to do that also with the ideal gas law. If we rearrange this to equal a constant R, P1V1 over N1T1 equals R, then any PV over NT should equal any other PV over NT in another situation. So my 1s here refer to an initial situation, the 2s refer to a second situation, and we're going to go over a problem with that. The last thing before we hit the problems is talking about STP, which stands for standard temperature and pressure. That pressure is 1 atm. That temperature is 0 degrees, but think of it in Kelvin because that's what you need, 273.15 Kelvin. What's interesting is if you use the ideal gas law and you plug in 1 mole and these conditions, what you can solve for is the volume of 1 mole of an ideal gas at STP, and you get 22.4 liters. What's really interesting is if you're talking about an ideal gas, which is one that which are the gases that we'll talk about in this chapter, no matter what the identity, neon, oxygen, carbon dioxide, no matter what the identity, 1 mole of any of those ideal gases will occupy 22.4 liters at STP. That's really interesting because these all have different masses. But if you have 1 mole of each of these, you will get a balloon filled to 22.4 liters at STP. We can use that to our advantage in just simplifying problem solving later. So we're going to apply the gas law, the ideal gas law and other laws, and we're going to solve some problems, and there are 3 types of problems. The first is just plugging into the ideal gas law. You solve for one of the unknowns under a certain set of conditions you're given. The second type of problem is this before and after. For example, V1 over T1 equals V2 over T2. Maybe the volume and temperature of a balloon changes in the morning and at night, and we can solve for some unknown in that situation. I have a problem like that. The last problem is just using a reaction and stoichiometry. Our first problem I call the plug and play, because you just plug in the numbers and you get your answer. Here we have a steel tank. with a volume of 325 liters. It's a steel tank, so this isn't going to expand or contract like a balloon. It's filled with a certain amount of hydrogen gas, and I give the grams. What is the pressure of the hydrogen in the tank at 24.0 degrees C? Okay, so pause this, try to solve this problem. What you're going to do is use the ideal gas law, PV equals nRT. R, go back and look at what that constant is. You would be given that number on an exam. And just be careful. Make sure your units are in moles and Kelvin. So go ahead and solve that problem and I'll go over it. Okay, so converting grams to moles, you basically divide the 53.7 grams of H2 by 2.016, which is the molar mass of H2. So in that molar mass, I've already incorporated the two H's, so its molar mass is always to 1 mole, and I get 26.61 moles of H2. Then go and convert Celsius to Kelvin, 24.0 degrees C, add 273.15 to get 297.15 Kelvin. Now plug everything into the ideal gas law, PV equals nRT. We're solving for pressure. Put in the volume, the moles, R, and notice I write out all the units just to make sure everything cancels, and then the temperature. Crunch your numbers, you get 2.00 ATM. So this is the first type of problem. Just the trick here is just make sure you're in the correct units. Sometimes you might be given pressure and you're solving for something else. Make sure if you're given torr or millimeters of mercury, you're converting that to atmospheres by dividing by 760, for example, millimeters mercury. Okay, here's our before and after problem. A balloon has a volume of 2.50 liters on a day when the temperature is 30.0 degrees C. Then at night, the temperature falls to 10 degrees C. The question is, what is the volume of the balloon? So just think about it in your head. Logically, is it going to expand or contract? You're going to get cooler. How is that going to affect the energy, the kinetic energy of the gas particles in the balloon? If it's colder, it should go lower, and the collisions against the walls of the balloon should be less. So I would expect we get a lower volume. Let's do this problem. How do we do this? Basically, you figure out what's constant. Obviously, pressure is constant. Something else is constant. Our gas is confined to the balloon. So number of moles is constant. So you need to think, okay, what's changing? Obviously, the temperature is changing, but the volume is changing. What law have you looked at where the volume and temperature changes? So think back on that. See if you could figure out this problem, pause it and work this problem, and then I'll go over it. So since temperature and volume change, but everything else is constant, you can use Charles's law. Or you could do something else. You can use this following equation that I showed you on the ideal gas law slide. The reason this works is, again, the PV over NT equals a constant, so PV over NT in any situation should equal PV over NT in any other situation. The way you use this is you just start here. This is just, you don't even need to know the individual gas laws. You can always get to them this way. If pressure is constant, that means P1 and P2 are the same and they cancel out because they're on opposite sides of the equation. Moles are the same, so those cancel out. So what you end up with, if you cancel out P and N, is V1 over T1 equals V2 over T2. This is from Charles's law. So even if you forgot Charles's law or you couldn't remember, oh, is it V times T instead of V over T? You can always just know this and come back to this and arrive at what you need by canceling out what's constant. Once you have this, then all you do is identify, okay, what's the initial volume, which is the ones. One is the initial state, and what's the final volume, which are the two. So initial volume and temperature is V1 and T1 here. which is the 2.5 liters, 303 Kelvin. And notice I just converted everything to Kelvin because we can't use Celsius. V2 is what we're solving for, and T2 is the final 10 degrees C, which translates to 283.15 Kelvin. So here my last sig fig would have been at the 1, but we're limited by 3 here. So then just plug in everything, solve for V2. So what I do is I cross multiply first and then solve for V2. I get 2.34, which is a smaller volume than what you started at, and which makes sense since it gets colder. Our last type of stoichiometry problem is shown here. And basically, stoichiometry problems talk about a reaction. So here's an example. How many grams of phosphorus react with a certain amount of oxygen at STP, so I'm throwing in an STP condition, to form tetraphosphorus dicoxide, which I draw here. But you could figure out the formula from the name. So your first step is to write a balanced equation. Then the only way to go from O2 to phosphorus is using the equation and mole ratio. So let me just give you a tip before you write the balanced equation. Phosphorus is special. It exists as a tetraatomic molecule. I think it's the only one that exists like this. So it exists as P4, similar to hydrogen existing as H2. So use P4, write a balanced equation, and try to solve this problem. So pause, and then I'll go over it. Okay, your balanced equation should be this. P4 plus O2 giving P4O10, tetraphosphorus dicoxide. The P's were balanced, but since I had 10 O's on the right, I needed to put a coefficient 5 in front of the O2 because 5 times 2 is 10. That balances the equation. Since you're given the amount of O2, to solve the amount of phosphorus you need moles, because you can only go between reactants by using mole ratio 5 to 1. So let's find moles of O2. There are 2 ways you can do this. You can, since I give you the volume, you need to use either the ideal gas law or standard molar volume from STP conditions. So if you use the ideal gas law, just plug in STP conditions, 273 Kelvin, 1 atm, the volume of the oxygen, and you can solve for moles. Or you can use standard molar volume, which is what I'm going to do. At STP, we know that 1 mole of any ideal gas occupies 22.4 liters. So I'm going to use that as a conversion factor. I started with 35.5 liters of O2, and then for every 22.4 liters, I have 1 mole. Crunch that number, I get 1.584 moles of O2. If you use the ideal gas law, you'll get something very close to this. Maybe the last digit might be different, but that's acceptable. Then use mole ratio, 5 to 1. For every 5 moles of O2, I need and use 1 mole of this tetraphosphorus. Crunch the numbers, you get 0.3170 moles of P4. And then since the problem really asked you to find grams of P4 needed to react with this much O2, you just multiply by molar mass. And don't forget you have 4 P's, so add up 4 P's and multiply it by your moles of P, and you get 39.3 grams of P4. Okay, that's where I'm going to end for part 1. Next time we'll do part 2 of the gases.